All right. Hi, everyone. I don't know if this mic is working. Can you all hear me? All right. It's so good to see you. I have to say, thank you all for coming here. This is amazing. So this is a dream come true for me, quite literally. I was actually imagining, hey, it's nice to have online HPG, but we should have something that brings us all together. And I'm so happy that you're all here. I hope you've enjoyed the food. Taipei, that was, yeah. I feel exactly the same way. I was also thinking, oh, this is a great food. I love this cuisine. I'm hoping that you all enjoyed it as well. But also, this was a restaurant by Syrian refugees, and we wanted to support them as well. So that was one of our motivation for picking this particular catering for us today. So I hope you all enjoyed it. So for today, that was one of our events. Our main event is going to be the keynote, of course. I'll let Angel do the introductions. A couple of things. This is our first ever event of this sort, right? So we have this online HPG followed by this in-person event, and I would really like this sort of tradition to continue. If you're going to continue having HPG online in the future, we should always have something that will bring us together in person. And we'll see how that will go. I will actually try to contact all of you via email, of course, and ask for your opinion on how HPG went and how this event went and what are the kinds of things that you would hope you would like in the future moving forwards. And we can continue shaping this conference in the way that we all enjoy and benefit from. One important note, one of the things we could accomplish this year was making sure that all HPG papers would be accessible freely online and not behind the paywall. So that's going to happen. It hasn't happened yet, but at least papers are online. So papers are finally online on ACM Digital Library, but they are currently not accessible freely. They're not open access, that's the right word, sorry. But they will be open access soon, so if you don't have access now, you will have access in the future. So hopefully things will be smoother moving forward in the future years so we can get them ready earlier during the conference as well. All right, I don't want to take all of your time because I am so excited about the next event that's coming up for the keynote. So I'll give the mic to Angel to do the introductions. Thank you all for coming again. Thank you.
Thank you, Jim. My name is Anjul. I'm one of the program co-chairs. The other one is Tammy Bubakar right there. We didn't want two doppelgangers to speak back-to-back, so I'm doing the speaking here. It's time for our first in-person HPG keynote in 3 years. And it gives me immense pleasure to introduce and invite Brian Karis on stage. For most of us, he needs no introduction, but just in case, he's an engineering fellow at Graphics and Epic Games. Most recently, had led the development of Nanite for UE5. Before this, he was mostly known for work on physically based shading and temporal anti-aliasing, although he has touched most areas of graphics in real-time computer graphics through his career. Prior to Epic Games, he worked at Human Head Studios, and today he's going to talk about Nanite. So I don't want to take much more time either. So Brian, here you go.
Thank you. Great to see you all in person after a long time. So thank you for inviting me to speak tonight. Most of you, I'm sure, have seen some demo of Nanite before. Maybe this one, or this one, or this, or some of the countless things that people have done with it since UE5 came out. I thought it'd be fun to show you something new, though, something you might appreciate more than the common audience. We got the Moana Island dataset loaded in UE5 running with Nanite and Lumen. This dataset has become notorious for being massive and unwieldy, and it sure is. There are 146 million unique triangles, 27 million instances, resulting in 164 billion instanced triangles. Now I have to caveat this by saying Unreal doesn't support PTEX, so we haven't imported any of the proper materials. This is all vertex color only. The water looks especially silly being flat blue. We also don't support curve primitives, which I'm told there are 10 million of them. That means that some of the trees look bare and there isn't any grass, but all the triangle geometry is present from the USD file. I've also lit it with a single directional light because our local lights couldn't handle this sort of instance count at the moment, but we'll fix that. We've just never seen anything like this before. With that out of the way, is it starting? All right, perfect. Here is a video of me flying around the scene at consistently over 40 FPS at 2742 by 1262 of the viewport. You can see there's just a tremendous amount of geometry here. These are like individual grains of sand. Right. We got little twigs here and needles. Like every leaf is actually geometry. There's no masked cards here. Pulling out a bit. See, the water here, although it looks flat, it's an 11 million triangle mesh. And underneath that water is a ton of detailed coral. Like, look at this surface. There's thousands of tiny little flutes sticking off of the surface, and they are all individual instances. This coloring, every grain of sand there is a separate instance. Each leaf is a separate instance. So last we'll cover the triangle view. These are all the individual triangles. And pull back here, like triangle dust indeed. So I thought it'd be fun to show you that, but I'm not going to talk tonight about what Nanite does or how it works. As a community, we talk a lot about what we invented and how that invention works, but we rarely talk about the process of inventing, the process of innovation, which is odd because that's the skill that we all practice. The course of technology and human knowledge is built step by step on what came before it. Progress requires understanding the state of the art, and engaging with that community is why we publish our work. But what bridges the gap between each invention is the inventor using their skill, making that progress. Not all progress is equal, though. Some invention makes large leaps and is incredibly disruptive. Those are what I'm most interested in. Perhaps I can stand on the shoulders of giants in terms of their process as well. What led to large leaps in the past? What differentiates good work from groundbreaking, evolution from revolution? It's usually easy to identify impact after the fact. Just look at the number of citations. But I want to know before that. I want to do more than just identify it. I want to know how groundbreaking work is done so that I can do it myself. Are there common patterns or skills? Can it be learned or at least fostered, or is it pure luck? I've found frustrating little on this subject that's worth reading, in my opinion. The best I've come across is Richard Hamming's lecture, You and Your Research, which I highly encourage you to watch or read a transcript of. I could regurgitate bits of his talk to you, but you'd be better off hearing it from him. There's a bit of it that I feel I can speak to, though. A question Hamming became famous for asking was, what are the most important problems in your field? Followed by, why aren't you working on them? I'm not sure how impactful and disruptive Nanite will ultimately be. Time will tell. But what I am confident on, though, is the importance of the problem it is trying to solve. So tonight, I thought it would be worthwhile to tell the story of my journey in trying to solve it, and along the way, tell you what I learned about both the problem and the process of invention of what ultimately became Nanite. So let's start at the source of it all. Before creating a tool, you must understand the people that will use it. Most of us don't think of ourselves as tools programmers, but that's ultimately what the majority of computer graphics is about, creating tools for artists to make art. So we need to understand artists. If your organization includes artists, talk to them a lot. Become friends with artists. Try to understand their process, what they spend their time doing, what was different between what they intended and what they actually created. If you don't have artists at your organization, watch videos of artists working. Watch instructional videos of how art software works. Look at breakdowns for how they made what they did. Many of you haven't worked in game production, so it might be worth explaining some of the problems that artists work with in my domain. You might be surprised at how much of their time is sucked up in technical tasks that aren't artistic. Laying out UVs, generating LODs, collision geometry, multiple versions of the same asset for different use cases, and then profiling and optimizing all of it to fit in budget. Optimization is familiar to anyone, but in games, it rules with an iron fist. I'm not sure how I can relay how dominant of a thought budgets are to artists any better than to tell you one of the most popular forums for game artists is called polycount.com. They name their website after the budget. And that isn't the only budget that they need to be concerned about. There are countless ones that dominate their every action. Polycount, draw calls, texture memory, mesh memory, light count, shadow casting light count, shader instruction count. Those are just the things that engineers can quantify and try to turn into a budget. There are 1,000 more things that an artist could do to make things run slower, and they need to know those things too. To make it orders of magnitude harder, there are many authors working simultaneously, often without context for where their work is going to be used. And that budget that they have to fit in, say polycount, where does that come from? Some engineer, like myself, had to pull a number out of their ass at the start of a project for brand new hardware that was faster than the last time. Ultimately, the real budget is the frame rate and the amount of RAM the machine has. All this leads to conservative behavior to avoid future pain. Going back and redoing things costs time and money. Oops. Sorry. In a production environment, money and time are just as much of a limiting factor on quality than rendering the pixels with the latest, greatest rendering technique. Anything that makes art more efficient allows artistic vision to be more directly expressed or enables more of the art team to contribute more widely because the process is less arcanely technical, will reap massive dividends. I argue there is no problem more important to work on in graphics right now than how to make high-fidelity content cheaper to create. But let's rewind. Back in 1999, I was a senior in high school. I was excited about graphics and knew that's what I wanted to do. I read an article about Messiah's character rendering tech back in the day. The game hadn't even come out yet, but this tessellation tech had already been heavily hyped. While I may not have understood all the technical details at the time, what definitely made an impression were the goals behind it. It automatically scaled detail based on the capability of your machine. The game would look even better on hardware that hadn't come out yet. There were no limits on the artist's models. Instead of creating 3 versions of every character for different purposes, the artist would create just the highest fidelity version. When I started my very first 3D graphics hobby project, I was inspired by Messiah to make my own adaptive tessellation tech. Yeah, from first triangle directly to view adaptive tessellation. I was going to use Rome to adaptively tessellate a mesh of Bezier patches, a terrain system on a mesh, basically. Rome is what is known as a right triangle hierarchy. Each triangle can split into 2 child triangles by bisecting its longest edge. By refining the tree in some areas and not others, it forms an adaptive tessellation. Where to refine can be based on both geometric error and size on screen, meaning it is view dependent. Anytime an edge is split, triangles on both sides of the edge must split in unison to keep the surface connected. It is only valid to split the longest edge. If the neighboring edge isn't the longest, then it is forced split until it is. This can cause a chain of forced splits. It isn't important to understand how my dumb code from high school worked. I'm only explaining a bit of Rome because it's going to come up again. Using Rome for Bezier patches was silly, but what did I know? I was just starting. The reason I'm bringing this up, though, is to illustrate that this problem inspired me starting from my very first 3D graphics code I ever wrote. I won't claim that it persisted in my head ever since. It didn't. But I believe that perspective on abstracting art authoring from current capabilities stuck with me. Fast forward many years, and I'm a professional game developer with a bit of experience under my belt. After shipping a game with no streaming and painful texture budgets, I read a post by Tom Forsyth explaining the math behind deciding which bitmaps are needed for a particular view. The texture size cancels out in the equations, which leads to an exciting, yet albeit common sense conclusion. The original size of the texture doesn't matter. Quoting Tom, it was a pretty cool thing to go and tell the artists that there are no practical limits to texture sizes. They didn't believe me at first. Nevertheless, if you have a streaming system that only loads the MIP map levels you need, it's absolutely true. So we built a MIP-based texture streamer, and I told our artists exactly that. They switched from 256 and smaller to 2K textures. Yeah, not quite. MIP streaming certainly was a huge improvement, but it didn't mean that texture size didn't matter at all anymore. That equation is correct, but it's making some assumptions which aren't true in practice. Virtual texturing addresses those issues by working on fixed size pages that are requested when they are sampled from. After seeing the results that id had with megatexture, I decided to write a virtual texturing system. While it was far more effort to make shippable than I expected, it was worth it. Removing texture budgets for artists was transformative. I could throw a bunch of numbers around about all the 4K textures we used back in the PS3 era, but none of that can explain how freeing it was for the art team, how much easier it was for onboarding junior artists, how much less wrangling there was required from the leads. I didn't do megatexture though, as in the virtual texturing system I wrote was only meant to be a really nice texture streamer. We weren't going to uniquely texture everything. Even still, there were bets with virtual texturing that I didn't yet. I only considered committing to ship to a VT system an acceptable risk because id was committing to ship an even more aggressive version than I was, and that means it's possible. So full megatexture seemed like an insane gamble from my point of view. It required an art pipeline that was very different from before and couldn't be realized any other way. The viability was based on numerous unknowns, each one an independent bet, all of which needed to succeed. The risk seemed massive, and going forward with it must have required tremendous courage. I've gotten questions about Nanite that are similar in nature to these, and I hope this talk can answer some of them. This is the same slide that I've used multiple times for talks on Nanite. It well summarizes the goal and the implications that it would have, that I always had in mind. The spark that started me seriously down this path was a comment from John Carmack in 2007. He said that the hope for their next iteration of their engine was to virtualize geometry like they had textures. He didn't explain how, just that he had some pet ideas. And with that, I was off to the races. I understood the impact that this could have. It was obviously one of the great problems of our domain. And if we, as an industry, were really on the cusp of solving it, I was determined to be on the forefront. This is a classic story of inspiration coming simply from hearing something is possible, even if it isn't yet. Why is that such a common phenomenon? I think it's because existence proofs give one a great deal of courage, and competition gives one drive. Both courage and drive are extremely important in solving hard problems, and I'd argue they're absolutely vital for attempting to solve the most important problems. To avoid giving the wrong impression, when I say I was determined to solve this, I don't mean that that's what I was working on at my job. I didn't have the luxury of doing that. Hell, I was still working on a virtual texturing system at the time. This was a background thread, what I thought and read about in my free time, basically as a hobby. This is a strange talk to give, and that the majority of what I'm going to tell you only existed in my head. So the first major solution I zeroed in on was not very imaginative, but I made the most obvious mental leap from virtual textures to virtual geometry, that being virtual geometry images. Virtual texture tiles are replaced by instance tile grid. Basically a train system on a mesh again, this time a quad tree. That implies it's a quad mesh, which would already often been the case with ZBrush models at the time, but those base cages aren't that low. I'd like to reduce anything down really far and not have to rely on the artist modeling things in a particular way. The point was for them to not worry about technical details like that. With a little bit of searching, I found this paper, which was close match to my idea. They formed a quad mesh through the act of parameterization with a goal of seamless texturing. The idea is that every texture chart generated by the parameterization can be topologically considered a polygon, with each polygon edge being the boundary to the neighboring chart. Any polymesh can be turned into a quad mesh through the same process Catmull-Clark subdivision uses. This was definitely more flexible in that the mesh could be turned into a quad mesh with potentially less quads because the quad count was proportional to the number of texture charts. This means that the artist wouldn't have to worry about that technical detail. A year or so later, I wrote up the idea in a blog post. A great thing about virtual geometry images being such a direct extension to VT is that I could easily extrapolate all sorts of things. Every stat about the VT system I could translate into geometry. In the meantime, John had talked about one of those pet ideas. A year after his initial tease, he explained his idea was raycasting sparse voxel octrees. He had made a different leap than I had from 2D to 3D. A few months later, John O'Lick, who was at IT at the time, did a talk at SIGGRAPH about this approach and showed a working prototype. Voxels would store the color and normal data that used to be in 2D textures. It's a binary voxelization, meaning voxels look like little cubes when you get up close. It's worth noting this was intended to be used for the geometric equivalent of megatextures, megageometry, so to speak, where the geometric and color data was unique across the whole world. While a few ideas were proposed for what would be done for animated geometry, the recommended one was to ignore it. Characters can stay simple triangle meshes. Based on the prototype, there were some assumptions that weren't acceptable for my goals. The memory was a bit concerning, but the biggest issue was the performance. It didn't appear to be fast enough if you assumed that it only appeared fast enough if you assumed that the majority of your frame could be spent tracing primary rays. No time was left for lighting and shadows. This makes sense relative to megatexture which baked lighting into the textures. The same was true for this demo. It was very impressive though, and I for sure kept my eye on voxels looking forward. As next-gen councils got closer and we started discussing developing a next-gen title, I felt my opportunity was arriving. I might be able to actually work on this for real. But there was also talk that it would need to be cross-gen. I had no faith that triangles proportional to texels were going to be shippable on a PS3. But there was something else I had come across that maybe could scale down, and that's progressive buffers. This is the first example of what I'll refer to as hierarchical level of detail, or HLOD. It isn't the first published, but it was the only one I was aware of at the time. HLOD is a hierarchy of triangle mesh chunks. Each level of the hierarchy is a simplified version of the last, using typical mesh simplification algorithms. A view-dependent cut of this hierarchy is rendered each frame. To make sure level transitions don't cause cracks, progressive buffers geomorph based on distance. If every vertex knows where it will move to in the next simplified level, it can make sure that it does so before that next level is chosen. That way there won't be any cracks. Because the geomorphing is purely based on distance, there's an assumption that everything in a LOD band is loaded. If a node at a desired level isn't present, there are problems. Progressive buffers are more like clip maps than they really are sparse virtual textures. And I want a sparse solution that adapts to visibility and where there's detail. I like the idea of HLOD, but I didn't like this specific crack solution. Why don't voxels have cracks? Sparse voxel octrees subtrees can be built completely independently without any knowledge of one another, and still not have any risk of creating cracks if one subtree isn't loaded. Maybe if I understood why, I could mimic it. The reason is that voxels are volumetric and can be no thinner than the width of a voxel. As resolution decreases, voxels inherently get thicker. Error is based on resolution and thus is less than the width of a voxel. Therefore, there can't be a gap between a surface stored at two different resolutions because the error must be less than the thickness. So to mimic that, we need to give the mesh thickness at least as large as the error. So we're borrowing another idea from terrain rendering. You'll notice a theme here. The idea here is called skirts. These are strips of triangles that go into the surface following the plane that the volume was sliced. They only drop far enough to cover a gap with their neighbor. But there's a massive assumption here. We have no guarantee that our meshes are manifold and can be operated on volumetrically. In fact, it is super common for game meshes to be open and also two-sided. But I ultimately didn't have a chance to pursue these ideas. The project never happened, and I joined Epic. The first big Question when joining a company, what should I work on? In the very first team meeting on my first week, I suggested that I could build what had been the most impactful thing that I had done previously. I could replace their MIP-based texture streamer with VT. The team's response shocked me. Nah, texture streaming isn't really an issue. Really? Yeah, it works well. What? Was their MIP-based streamer that much better than mine? Did I come to a faulty conclusion because my code sucked? It was probably the second largest investment in a single system I had done up until that point, and it was a mistake. I don't think I'm particularly prone to imposter syndrome, but it is really easy to fall into this trap when joining a new team. Okay, that's fine. There's a ton of other things that I can work on where I think I can provide value. The next surprise. Little did I know that Epic had been researching virtual geometry 2 in the early days of UE4. Specifically, Andrew Scheidecker had been working on multi-resolution meshes. The research had been shelved a year or two before, but serious investment had happened. Notice the same high-level goals are listed as what I had previously. Andrew's approach was fairly similar to the virtualized geometry image idea. The geometry images were wavelet encoded, basically deltas from the previous MIP, but he was more ambitious than I was, or at least expecting more hardware capability than I was. The plan was for this to be a full raise-style rendering with micro-poly shading and software rasterization. But most interesting to me was the approach taken to build the data. He was using maps. The foundational concept behind maps comes from the field of topology. You may have heard before that a coffee mug and a donut are topologically equivalent, but we can say something stricter than that. A mug and a donut are homeomorphic. Two surfaces are considered homeomorphic if there is a continuous invertible mapping between them. That is exactly what we want to be able to displace one into the other. Maps is an algorithm for simplifying a mesh while maintaining the homeomorphic mapping of surface points on the simplified mesh back to the original. With that information, the simple mesh can be tessellated and displaced back to the original surface. But that assumes that a very simple mesh exists that is homeomorphic to the complex one. And that is not true for all cases because a simple mesh must have the same genus as the complex one. This chain has a high genus. There is a limit for how far we can simplify it without reducing the genus and breaking the ability to displace back to the original. You can see a simpler example here. The mapping of geometry images doesn't have this problem because it removes a constraint. The mapping they seek is a topological equivalence to a disk. The boundaries of the image are free to match up fairly arbitrarily, so the key thing is to find out where to cut the 3D surface so that it can be unwrapped to a single 2D image. This mapping is still invertible and is continuous in the direction of low to high. It is no longer continuous from high to low because of those cuts. Cuts are required for any mapping between a closed 3D surface and a 2D domain. Maps can be continuous in both directions because it is a mapping from a 3D surface to another 3D surface. Genus is only the beginning of the problems, though. Both of these approaches choke if the surface isn't connected. A continuous domain can't be mapped to a discontinuous domain without introducing discontinuities in the mapping. If this chain is modeled how it actually is in the real world, where each link is an independent piece, we're screwed. The overall lesson here is that we cannot assume topology is simple, connected, and low genus. Geometric detail can't be represented only as displacement in all situations at all scales. The second issue I heard more from the artists who had been playing with these prototypes. They really didn't like the fact that their art was being resampled and the details they had fussed over were being lost. No matter how close they got, it never looked exactly like what they had modeled. This problem is basically aliasing, and in the case of vector displacement can be improved somewhat like what's on the right, but it only goes so far. With these insights in hand, I decided to seriously explore irregular meshes and HLOD. From my previous research, the key problem is cracks, so I'd focus specifically on evaluating all potential solutions to that problem. A friend of mine taught me an exercise to use when exploring a new design space. Visualize the multi-dimensional space of possibilities you are trying to optimize. The dimensions may be discrete or continuous, but the point is to identify them and explore their limits. Even if the manifestation of some option isn't apparent to you yet, the relationship between those that are may point to a hole where something must be. Think of how the standard model of particle physics predicted many not yet discovered particles because there are holes in the map for a particular combination of properties. Let's pick an abstract dimension to start with and explore its limits. What's the least amount of knowledge neighboring clusters of triangles must have of one another and still guarantee no cracks? Just a spatial constraint. We trade the information for constraints. If the geometry expresses a volume, the constraint can be a plane cutting into that volume. This is what the skirts are that we covered earlier. Can we use skirts at any boundary? Unfortunately, no. The constraint is a plane, or more specifically, a planar face of a clipping volume that divides this cluster from the others. The volumes don't need to be boxes. They can be a general tetrahedralization to divide the space. But we can't just use any boundary edges that zigzag. The virtual cutting faces would only be as wide as the edges themselves, which is effectively the same as locking them, making the skirts pointless. What do we mean about knowledge of neighbors? The absolute least amount of knowledge at build time is none. Ignore completely what your neighbor is doing and move the boundary vertices around however you like. But then we need to do really heavy work at runtime to stitch boundaries that don't match. This is basically the most knowledge required of neighbors at runtime. Well, on opposite ends of this dimension, both skirts and stitching could also be categorized as approaches where the boundary edges don't match. Stitching seals the gap at runtime, skirts seal the gap at build time. I believe those are the only two geometric options for allowing boundary edges of the pre-computed triangle clusters to not match. That means all other approaches must create matching boundaries. The most obvious way to make the boundaries match is to never change them. This is the least information, heaviest constraint solution with matching boundaries. It's garbage, though, and fails at heavily reduced levels once you run out of non-boundary edges to collapse. Worth noticing that the matching is going up in detail. How about the opposite direction? If the resolution of the neighbor is known, we could reduce our boundary to match it. This is the approach taken by both geometry image quad trees and progressive buffers. Like progressive buffers, boundary vertices could store the position where they move to in the next coarser level. They would also need to store which neighbor that they border. And at runtime, a node would need to know each of its neighbor's levels. And the tree would need to be restricted such that there isn't any more than one level difference between the neighbors. But we can also make a trade here for less information and more constraints. If the tree was a spatial subdivision, say an octree, then some of this data could be implied. The neighbors of an octree node are implicit and wouldn't need to be stored. The verts on the boundary of the octree node can be implied from their position. Which neighbor those vertices need to match could also be implied from which face they touch. I said before that progressive buffers were like a mesh version of clip maps, but they don't need to be. They could be made sparse by adding a clamp to the geomorph to be no more detailed than their neighbor. So far, we've been assuming that the data of a node and the hierarchy is independent of all others. For boundaries to match means they have to duplicate vertices of their neighbor. Seems like an approach that requires the most information is one that directly indexes the neighbor's vertices. It's a bit of a stretch, but I think the closest are probably view-dependent progressive mesh approaches. They record and play back the finest granularity of edge collapses and splits, just like progressive meshes do. But they handle being applied out of order or incomplete to account for view dependence. By applying and removing these operations, we change the mesh just like the simplifier would have done offline. At no point can there be cracks. They operate at a really fine granularity, though. Making decisions per vertex is pretty excessive. Compared to VT, this would be like streaming texture data at the granularity of texels. That's not to say that these collapse and split operations couldn't be batched together. But there's a trap that we've fallen into that's easy to do. And that's equating the data that is resident in memory in a renderable form with the data that will be rendered. Work to address cracks only needs to be done when level of detail changes. That's technically true. But that's not the same thing as when data is streamed in. There may be many instances of that model in the scene. Not all of those should render the highest detail resident in memory. While these progressive mesh approaches don't require that the update operations be at streaming time, they do require a persistent version of the mesh stored at the last scene detail level. Each frame, it will be updated based on how the view has changed. That kills instancing and is simply too much memory. We haven't encountered a method for handling cracks like Rome yet. Why does that work? The trick is that not all sides of the triangle split at the same time. Only the longest edge does, and which edge is longest at each level must cycle. The two right triangles that share their longest edge are dependent on one another. Each can only refine if the other does as well in unison. For this level transition, the shared boundary between them is essentially internal because they act as one. Anything internal can be modified without danger of causing a crack. We can apply the same concept at a larger granularity and make triangular shaped clusters. This is basically what batched dynamic adaptive meshes does. Compared to Rome, we can see the power of irregular meshes to achieve lower error at the same number of triangles. So far, we've seen dependent nodes need communication such that they act in unison. That's unnecessary. So long as they use the same data to decide, they will decide the same thing. BDAM uses another trick to avoid communication. Remember, those forced splits might be necessary in Rome and that they can recursively chain. Why did one branch of the tree refine further than the other to get into this situation in the first place? The reason is that ancestors on that branch of the tree might not have reported such a large of an error. So they stopped refining once the error was good enough. Only when it gets to this level is the error known and it would want to split. We can just tell this branch of the tree that there's higher error at a deeper level during the build and bake it in. What this is doing is enforcing that the error function is monotonic. These two things together mean that no communication is required between nodes, and that makes it easy to evaluate in parallel, so it should be easy to port to the GPU. So far, that is only good for terrain. Is there a 3D analog for right triangle hierarchies? Yes, tetrahedron hierarchies called tetrapuzzles with longest edge bisection. All tetrahedron that share the common longest edge form a diamond, and they are dependent on one another. Just like before, these dependent nodes must refine in unison. That means any edges on the boundary between these nodes are free to move. Unlike before, the shape of the diamond is not always the same. There are 3 different types that are cycled between, but regardless, they're always formed by the tetrahedrons that share the same longest edge. There's an issue here that also existed for progressive buffers. It is a problem with any regular spatial partitioning, whether it's octree, right triangle hierarchy, or tetrapuzzles. The number of triangles per cluster is dictated by the spatial size of the node. It is entirely possible that only a single triangle falls in a tetrahedron. That cluster would be very inefficient to render. A surface could wave in and out of a partition, which would mean lots of non-contiguous triangles and excessive number of boundary edges, which would need to be locked. Triangles in typical meshes are not uniformly sized or distributed, so there's no reason to believe that a particular level of the tree will have a specific size of triangles. In fact, this is an important point with most massive model visualization research. Most test with laser-scanned sculptures, which have very uniform triangle density, and uniform density is not a fair assumption. Just like before, we can reduce constraints by adding information. Instead of some of the nodes being implicitly dependent on one another, we can store the dependent nodes explicitly. This gives complete flexibility over tree building. Both quick VDR and batched multi-triangulation take this more flexible approach. The spatial schemes could store their data in the same data structures, their implicit rules stored explicitly. In fact, because of how dependent nodes are enforced and how the tree restriction is addressed by making the tree monotonic, there isn't actually a difference in how the data would be stored or how the runtime algorithm would work. They are essentially all the same data structures and runtime algorithms. The difference comes in how the data structures are built. Looking at it in this generalized way allows any number of variables to be optimized for. For example, number of triangles per cluster or minimum number of locked boundary edges. So out of all of the irregular mesh choices, this appears to be the best. No assumptions about the mesh's uniformity or anything about it being closed or having thickness. Coarse granularity LOD and occlusion decisions are well suited to run on the GPU. Anything complex to address cracks is handling during the build, not at runtime. Large batches of triangles are rendered directly. Triangle data is touched once and doesn't pass through memory many times. Triangle clusters are stored completely independently of one another as just raw triangle data, so any form of general mesh compression can be applied to the clusters so long as their boundaries match. And lastly, there's no problem with sparse residency. With all this focus on high poly meshes, nothing I've explained so far really addresses draw calls, unless you assume it's all unique geometry and textures, which I am not. Draw calls are just as much of a problem for artists as poly count and are a core aspect of the geometry problem. That problem isn't just a tug of war between detail and cost. Optimizing for draw calls controls how a scene is built because it dictates the granularity it is broken down. Should a bookshelf full of books be merged into a single mesh? But what if we need many bookshelves? Do they all have to have the same arrangement of books on them? What if there needs to be these different bookshelf variations, just so that there are different arrangements of books, but that means that there's more memory. So coarser granularity is best for performance, right? Not necessarily. Too coarse and the culling is inefficient, since draw calls are the culling granularity. And none of this is necessarily the granularity that is most efficient for an artist to author. So another important part of the virtualized geometry goal should be that there is no performance penalty or quality impact for scene construction decisions. There should be no ideal size or imposed granularity for breaking up the scene. For this reason, and many more, I want to decouple visibility from materials. I also only want to rasterize the triangles once per frame, and pixel quad inefficiencies can get really bad with small triangles. So drawing on my experience from VT, I figured the best solution was to cache material evaluation into a virtual texture. This is similar to texture space shading, but does not include lighting. What would be stored in the VT would be a compressed G buffer. My understanding is that true texture space shading needs to be, my reasoning is that true texture space shading needs to be updated every frame and doesn't benefit much from caching. Object space solutions in any form overshade, usually by a substantial factor, 4x or more. Texture space shading approaches also don't avoid pixel quad inefficiencies unless you also keep around a heavyweight texture space visibility buffer. Geometry data, on the other hand, should be able to cache and persist. Maybe that could mean that another artist budget could be crushed, that being material shader cost. When rasterizing the triangles, all that would need to be output per pixel is a physical texture UV. The idea is incredibly similar to what Sebastian Antonin described in his SIGGRAPH 2015 talk, but we arrived at it independently. So to summarize, at this point in time, I was converging on something I thought would work well. HLOD following a scheme like quick VDR, except all the logic would be moved to the GPU. This allows occlusion culling against previous frames depth buffer, which I had already had great success using HZB tests years before. The triangle clusters I intended to draw all with a single draw call using this new multi-draw indirect functionality that I had read about. And the G buffer would be cached in texture space and only sparsely progressively updated. I talked up wanting to work on this, but there were other priorities at the time. But folks knew that I was interested in geometry stuff. So when a new project popped up that had some interesting geometry problems, I was asked to join. The Geometry 2.0 term originally referred to geometry editing tools intended to finally replace the super ancient BSP editing that had been around since UE1. There was a new idea of a future-proof model format, also being referred to as Geometry 2.0. See, typically every new game project builds all of its art from scratch. even if it's a sequel because graphics technology improves enough that old assets don't have enough fidelity anymore. The idea here was that assets should be authored once at an archival level of detail and then never would need to be remade. The same idea is coming back around. The perspective of those that had been working on this was that higher order surfaces, specifically Catmull-Clark sub-D, there would never again be a point where old assets could look low poly. And with hierarchical edits, basically a form of sparse displacement, all types of things could be expressed. There are also many other things from both tool side and rendering that could use improvements as well. If we're going to start with a clean sheet of paper, maybe we could address those things too with this new approach. I won't go into all the details of everything it was trying to accomplish, but suffice it to say the problem was over-constrained. Just an example of one issue we ran into trying to solve all these things with one approach. Those old BSP modeling tools we were looking to replace were at the heart CSG. Replacing those couldn't really be done without regressions unless the new modeling tools also supported a form of CSG as well. But the intersection of two Catmull-Clark surfaces doesn't result in a Catmull-Clark surface. CSGing their control cages doesn't give a result that is even close to what you'd expect. But we couldn't just CSG the surface subdivided at a certain level because the original goal here was that there wouldn't ever be a resolution that would one day not be enough. There were many issues like that. Eventually, the project was put on hold. And unification can be a honeypot. It is often a nice guide, but taken too far, it can make everything worse. The advantage of unified solutions is a single piece of code that can be invested in. The point is to reduce work. This is all good, but when pushed too far, the unified perfect solution that solves every problem simultaneously can become so insanely difficult to find or execute that you spend more time seeking it than it would take to write multiple specialized solutions. It's a form of the old saying, perfect is the enemy of good. The unified approach to tools can also mean a more consistent user experience. There aren't silos anymore. Skills that are learned in one area can transfer. But sometimes there's a right tool for the job. All of this had been predicated on Catmull-Clark sub-D being a good solution for future-proof modeling. But does adaptive sub-D even solve this? I talked to our artists, and most of their control cages were higher than the game meshes they were currently using. In film, they're an order of magnitude worse. That can't be the lowest detail that we render. Sub-D is amplification. A simplification solution would have been needed in addition. Two different, very complex solutions, one for up, the other for down, pretty obviously out of the zone of elegance and unification. Funny enough, simplification all by itself is elegant and unified. A static mesh can be subdivided offline, and one method can handle both up and down. The sad thing is I already knew that. I said as much in that blog post back in 2009. There was an important lesson here that I have tried my best to adopt. No one I was working with had walked the path that I had already, and we were repeating numerous of the same mistakes I had already made, and I didn't say so. I didn't argue my perspective. Like before when I had joined Epic, I was joining an established group of what were clearly very smart people, and I wasn't comfortable with challenging the high-level direction. I needed to get past discomfort and teach others what I knew already, because I definitely knew a thing or two about geometry by this point. I've continued to be surprised throughout my career about my expertise versus others. Don't assume you either know more or less than others. I guarantee you at some point you will run into someone that knows more than you on almost any one topic. And you'll be surprised at what luminaries in the field don't know. The only way to get at truth is to say what you think you know without fear of being wrong and without expectation of being right. Either it's an opportunity to learn or an opportunity to teach. There's no shame in either. Being wrong is not nearly as bad as you'd imagine it to be. It's the state you are before being right. One of those things I knew all along was that MIP-based texture streaming doesn't scale. Turns out it was a problem in Unreal 2. The engineers just weren't hearing the pain. Regardless of whether VT was a good idea before, it was clear it was going to be important in the future because SSDs were now commonplace. I was convinced at this point that virtualized geometry was going to be the next big thing. In general, large data, fine-grained streaming data compression, and general data virtualization was the key for a big jump in fidelity. But we still didn't even have the last generation of virtualized data. We need virtual textures first. So I worked on that for a bit. In the meantime, new exciting work was published that changed the landscape. Most directly related was triangle cluster culling, which was a finer granularity than I had been considering and should be a drop-in replacement for multi-draw indirect batches. But there was also exciting stuff with voxels and point-based rendering in dreams. I had informally arrived at some requirements for a solution through this process, but it's worth formally stating them. I can't completely change all CG workflow. The vast majority of modeling and texturing will happen outside of Unreal. I don't have any control over that data format. Users may import CAD models or film assets that were authored primarily for a different renderer. Some will have UVs and tiling detail maps. From the user's point of view, this new virtualized geometry tech should slot in exactly where static meshes do right now. As an aside on UVs and data reuse, academia too often conflates texturing with painting a mesh. 2D textures are very often used more like wallpaper than paint, and controlling their placement requires editing UVs. The best demonstration of this that I can think of is the sci-fi lab created by Tor Frick. The entire level uses a single 512 by 256 texture. While this example is a little old, and this amount of memory optimization is extreme, the general technique used here is used everywhere in games. Looking at something a bit more modern, the carbon fiber here is a tiling texture, the brushed metal is a tiling texture, and controlling its orientation matters. Model instancing is how we reuse geometry data. In John Carmack's argument for unique texturing, he said texture tiling is just a limited form of compression. He's correct, but it's also a damn good form of compression. It is very common to reuse the same data thousands, if not millions of times across a game. There is no generalized image compression that gets ratios like that. Reuse is what enables miles of ground with fidelity of pebbles. So long as the entirety of a game needs to be delivered to the player up front, data reuse like this will be essential. So the next requirement is that it supports instancing with arbitrary instance transforms and is not a unique world space data structure. Lastly, it needs to be fast. I expect many next-gen games at this point will be 60 hertz. That does not mean that we have 16 milliseconds to render geometry. Many methods claim to be fast, but take the entire frame just to draw colored surfaces. I expect a similar frame breakdown as what we had before, so less than 6 milliseconds to draw geometry with materials on it. Counting for material shader evaluation, this means probably 4 milliseconds or less for the geometry portion. Those are the hard requirements, but it's worth prioritizing the soft goals as well. Taking a lesson from Geometry 2.0, do not try to solve everything everywhere all at once. Plan stepping stones such that there can be a success along the way to the ultimate goal. Those successes will boost your confidence and the confidence of your superiors, meaning less chance that your project gets shut down. Ideally, if you can get intermediate results into artists' hands, you will learn things that you didn't previously know. So to this specific problem, the area with the biggest geometry budget issues is environment art. So priority number 1 is virtualized geometry for what are now static meshes. Deformable geometry and animated characters would be second and should ideally follow from the extensions to the same system. It doesn't need to be solved immediately, but it needs to be conceivable that that the path that we are on will lead there. Third is terrain. While improvements to rendering quality and tooling for terrain would be nice, that isn't the goal here. Terrain authoring doesn't really have budget problems. Maybe a shared solution can be used for all of these issues, but it's far too difficult of a problem to introduce additional constraints or distractions. Through shipping Paragon, I was given a lesson in how prevalent view-dependent animating and non-UV-based materials are. The surface caching idea assumed a limited number of pages would need to be generated each frame because they're mostly cache hits. But all these things invalidate the cache, which would result in tons of new pages every frame. I expect it would be common to shade more texels than pixels with this route. The alternative is to output a visibility buffer. We lose any chance of addressing those material shader budgets, but that appears it wasn't reliable anyways. So visibility buffer checks all the other boxes. Then opportunity struck. With the coming next generation of consoles, it was decided that there should be a full version bump of Unreal Engine. There was going to be a UE5. I joined Epic after UE4 had been unveiled. I contributed to its evolution, but not really its initial design. The mission of UE5 and defining the next generation of real-time graphics put lofty expectations on this, unlike any I had ever worked on before. While I had talked about hugely ambitious goals earlier, this was the point where the weight of the opportunity really sunk in for me. This was the next generation of Unreal. UE5 must be obviously a generational leap better than UE4. A laundry list of miscellaneous odds and ends is not good enough. This was our definitive moment to make a statement to the world what the next generation of games will look like, and this was my moment to present my vision of the future of real-time computer graphics, and I need to live up to that. Collaborating with others, we wrote up a tech direction that is surprisingly close to where we've ended up. My piece de resistance was virtualized geometry. I argued that there was a good chance that now was finally the time that this could work, and it was worth taking that chance. With that, I got freedom and a timeline that was unlike any I had ever had before. My full-time job from that point on, with few exceptions, was to R&D virtualized geometry. In the process of trying to sell this vision, I searched for images that exemplified what could be done if this problem were solved. With it, one could perhaps imagine our next tech demo. I found some amazing concept art from the artist Alan Way, everything covered in thin pipes, trusses, and buttresses. It's both perfect from extreme geometric complexity and would likely kill the thing I had planned to create. As I mentioned earlier, most of the existing research tested with laser scan sculptures. These meshes are fairly smooth. They can hit 1 pixel of error with average triangle sizes that are considerably larger than a pixel. I feared that was not the case here. These surfaces are not smooth nor continuous. I have no reason to believe that I'm going to be able to rasterize pixel-sized triangles. There's a major performance cliff with hardware rasterization at that scale. I do not want to invest heavily in tech that can only make lumpy rocks. That was a big reason why I steered away from geometry images and displacement towards irregular meshes in the first place. I want to solve hard surface and mechanical as well. But if mechanical fails when pushed too far, it's not really solved. So I'm certain triangle cluster rasterization based will work, but not to the pixel level. Will something else? I could have plowed forward with that idea, but that I had and I was confident was good, but the weight of UE5 caused me to hold off and explore alternatives. The first I considered was ray tracing instead of rasterization. Log n means ray tracing scales really well to complexity, but it still scales. Just to get to 1 million triangles in a scene with a 4-way BVH, you'll need to have 10 dependent loads, 15 to get to the 1 billion triangles. It's important to note that this was before I had any sort of RTX hardware to test. I don't remember whether I even knew if it was coming yet. But what had just been published was Oculus Research's hierarchical raycaster. This was basically hierarchical packet tracing. Any levels of the tree that will be redundantly traversed for some group of rays can be done so once for a frustum bounding the rays. Essentially, it's the same BVH concept, but for rays. Not a new idea, but the 10 billion rays per second number that they were touting certainly caught my attention. Experimenting with it made me conclude that these numbers were highly dependent on triangles covering many sample points. For VR applications, that may be true, but not very helpful for pixel-sized triangles. I realized that if the key task was to pick out which of the very tiny triangles lands on the pixel center, then a hierarchical rasterizer could be written as well. I'm not sure if such a thing has been published before, but the idea is instead of traversing the scene BVH once per ray, you would traverse it once for the entire frame. Continue on to a node's children if they project on screen to cover any pixels at all. A regular raster grid makes intersecting pixels simpler than arbitrary rays, frustums, or cones. Occlusion is more difficult but possible. But the idea of picking out one triangle for this pixel, then skipping over thousands before finding the next triangle is Kashmir City, clearly inferior from a performance point of view to LOD. Besides, LOD is needed for streaming anyways. log n cost of tracing, but linear scaling in memory. We need to, like, we're wanting to virtualize geometry, right? And the BVH data is not cheap either. R LODs are an interesting hybrid, but then the log n part isn't that relevant anymore. With Dreams showing great success with points and Atom View showing some virtualized geometry-looking stuff animating, I thought it was worth taking a look at point-based rendering. Easily supports animation is incredibly appealing, and I had no doubt that atomic scattering points on screen was fast. I had heard an encouraging thing from Jerome, our art director, that when he worked at the Digimat team at ILM, V-Ray proxies changed their world in terms of dealing with geometric complexity. Memory was more of an issue for them than render time, but once they started using V-Ray proxies, they stopped having to worry about running out of memory. Turns out this magical feature was a far more simple Surfel representation than I expected, given the results he claimed. A really nice thing to see was that the Surfels were parameterized. They were decoupled from the material, which could be swapped. That's exactly what I need as well. There are many different types of point-based rendering. What I was interested in was scattering infinitesimal points to the screen using 64-bit atomics. The work per point is the least possible, a matrix multiply and a pixel rate. Points can be guaranteed to be no further apart than 1 pixel, so there aren't any holes. But I'm not sure it is practical from a performance point of view, but that doesn't really make sense for animation unless the points are dynamically generated for something else. So let's assume some amount of hole filling. The first problem that comes up is, what does anti-aliasing mean when points are binned? A point doesn't have a shape that a pixel center intersects. Instead, the point's position is quantized. Thin features become as thick as 1 pixel no matter how far away they are. So thin wires appear to get thicker the further away they get. This is the same problem with pixels, by the way, and it looks bad. Could pre-filtering solve this? Points could have a coverage associated with this MIP level. While true, that doesn't provide interpolation between points. Binning points is actually equivalent to nearest neighbor texture filtering, just in reverse, if you want to picture what sort of artifacts these look like. So we can have MIP maps with points, but no bilinear or trilinear filtering, so that wire isn't going to appear to get thinner until it jumps to the next MIP level. That is, unless that's done stochastically. I didn't really think of that at the time, so it might be worth looking at again. Hole filling makes this stranger yet. I concluded that the points needed to represent a real continuous surface such that AA can do real intersections. Scattering the points to the screen just seeds data for a screen space pass to connect them and complete the surface. The idea was that filling in post using gather would be faster than scatter by rasterization. But what defines a hole? Was it supposed to be there or not? If all gaps of a certain size are filled, it's going to look blobby, like as if there's surface tension. If I can store something about where the holes should be and shouldn't be, how about storing the distance from the furthest point that it should be connected to? Turns out the idea of seeding the screen and completing the surface in post is faulty because of aliasing. A simple illustration of this is the dartboard configuration. 2 points can land in the same pixel, the smaller in front of the larger. The larger needs the behind surface to be filled in, but that information is lost because the closer point won out. While this is probably reason enough to kill this, there were more problems. The original interest driven by animation being easy doesn't work either. There are no bounds on how much animation can stretch a surface, which means there's no bound on how far apart points can get on screen. If something else was generating the points on the fly, then maybe stuff like this could be addressed, but point clouds are not a robust data structure to express surfaces by themselves. Carrying the connectivity metadata idea further devolved into storing the point indexes of neighboring points that the hole filling should connect to. Basically just reinvented triangle meshes and index buffers. All this was a ton of screwing around just to try to do that connection in post. But honestly, would it really be that expensive to do it during the scatter? Could fill in the pixels in between 3 points, a triangle rasterizer? At this point, I was approached by Michael and Teen, who was starting on the beginnings of what would become UE's new physics system. He said that in film, it was a big pain that there always needed to be a dual representation. Rendering worked with explicit surfaces and simulation with implicit. A world of possibilities might open if there was a single geometric representation, an implicit surface. By that he meant signed distance fields stored as voxels. There are numerous other advantages that appealed to me from the rendering point of view, and I had not seriously explored voxels yet. Naturally supporting incoherent secondary arrays is huge, but also cheap collisions and with all sorts of shapes, CSG, and in theory, level of detail is simple. Overall, I didn't believe it was going to work out, though. If it did, the rewards would be huge, so it's worth considering, but the goal in my mind was to rule this out quickly. My biggest concern from the onset was data size. Surface data scales quadratically with resolution, but volume data scales cubically. SDF adds more data to voxels not only from distance values, but also that at least one value on either side of the surface is necessary to interpolate to 0. An SDF does address a few issues with voxels, though. What does it look like magnified? Binary voxels are cubes, and that is no good. Same goes for attribute data. We would like to have texture filtering. The second is the anti-aliasing issue I mentioned earlier. Signed distance means a sloped edge can be a straight line, not a stair-stepped one, and that can help edge quality. Because of the data issue, I think the only way that this is going to work is if I store only the narrowest band data per MIP level. By that, I mean only the values immediately on either side of the surface. So what resolution is needed? This is a 2 million poly bust resampled to 13 million narrow band signed distance field voxels. Even though there's far more value data than the original, it still looks blobby. Artists didn't like resampling, and this is why. Signal theory tells us that there will be loss of high-frequency details for any resolution less than the Nyquist rate. Or in other words, voxels must be half the size of the shortest triangle edge or less to not lose detail. That would be an insane amount of data. Adaptive resolution can help. Higher resolution is only needed where high-frequency data is. The irregular mesh was obviously doing that. Adaptive distance fields are already a well-known solution to this problem. But even with perfect adaptive resolution, the Nyquist rate still means that 4x the number of voxels as vertices are required. That ignores the data required to express that adaptiveness, i.e. where voxels are and aren't, which is not free. The difference to mesh compression at this point starts to shrink. I won't argue that they're equivalent, but at least there is a good deal of effort and sophistication is required to beat meshes when attempting to store geometry which was originally authored as a mesh at some definition of lossless. So my conclusion was that MIP0 data, so to speak, is best to retain in its original format. Either that means switching to rasterized triangles when close enough, which kills all those advantages that voxels had and means multiple rendering paths, or the triangles need to be voxelized on demand and cached for the finest detail levels. That effectively provides infinite zoom without ever needing to see voxels get large on screen. A similar thin feature problem I mentioned with points happens here too. With SDFs, those features will vanish unless a voxel center happens to land inside the surface. Analysis can be done and the SDF can be modified to grow such that it doesn't vanish, but features thinner than the width of a voxel at that level of detail are not expressible as an SDF. Voxels would have to express some sort of coverage information to handle this. Is that in addition to the signed distances or replacing them? This seems like just an issue with those little spindly details, but at some scale, every wall falls into this case. The thickness of a wall will need to be artificially increased or the wall vanishes. Attribute data has issues before then. As mentioned, signed distance value is required on either side of the surface with opposite signs such that there is a point where they interpolate to 0. Only one negative value is needed in between two positive for the thinnest surface, but 2 internal values are needed to reliably interpolate attribute data. A wall needs to be able to support 2 different colors on each side. Having only one color in between them means leaking. So that means surfaces need to be at least 1 voxel thick to exist and 2 voxels thick to not leak attributes. Alternatively, attribute data can be stored in a directional basis, but that significantly increases its footprint and would often be worse than just increasing the resolution to fix this leaking. Speaking of attribute data, not all of it is filterable, specifically UVs. UVs have seams, and filtering across a seam is invalid. Filtering within a chart is required to be continuous. So that means some sort of discontinuity information needs to be stored to say which neighbors it can interpolate to and which it can't. That might solve the leaking issue as well, but how simple can that data really be? If we want UV seams to not stair-step either, now there needs to be some sort of SDF of the UV chart boundary. Yikes. Should also consider some future requirements. Don't need to solve these yet, but does there even seem like there's a path there? Can we deform and animate voxels? Yes. Some research has been done in regards to deforming the incoming ray instead of the geometry. How controllable that is for a rigor's purposes is unknown. How about morph targets? I mean, maybe you could do some sort of advection, but no. Morph targets only really make sense for explicit surfaces. How about displacement maps? Same thing. A different form of procedural geometry could be done in SDF space, but that wouldn't really be portable like displacement maps are. All right, it's time to build a prototype to test the performance. The approach I experimented with was inspired by both Dream's brick renderer and OpenVDB. Bricks are scattered to the screen. The simplest form of this is rasterizing a cube per brick. Within a brick, I do a short raycast through the brick data. This is a very effective empty space skipping technique, and it has the advantage of supporting arbitrary transforms at the scatter phase for little cost. A hybrid scatter-gather doesn't require the data to be stored as bricks. It could be any sort of tree. Storing the data as bricks avoids pointers near the leaves to save space. But full bricks of value data are likely even worse than that. I don't only want to store the narrowest band within the brick. Instead, I'll store a bit mask for voxel occupancy. A uint64 expresses a 4x4x4 bricks occupancy. The value data can be packed and indexed using a prefix sum of this bit mask. Not having a dense SDF sort of rules out sphere tracing. Instead, a ray can be marched through the brick using DDA, checking a voxel bit at a time. Only a single uint64 read is needed for the entire ray march through the brick, which would mean this should be really light on bandwidth. Once an occupied voxel is hit, the SDF values could be read. These occupancy bits aren't actually one-for-one with the value data, though. They instead are the voxels that the surface intersects. The SDF values are on either side of the surface. They are the four corners of that occupied cell. The SDF is interpolated within the cell, where at some point it will cross zero. To make the bricks bigger and to get a little bit more gather and less scatter, I added one level of hierarchy to the bricks. So instead of 4x4x4, they would be 4x4x4 bricks of 4x4x4 voxels each. So 16 by 16 by 16 in all. That means a hierarchical DDA, again like OpenVDB does. So a few optimizations to this that others may not have talked about. Most bricks are sparse. The box used when rasterizing them can be shrunk to fit the occupancy bits. Finding the bounds can be done with some bit fiddling. Or with a bit more memory, the bounds can be shrunk to the exact surface of the brick. Once an occupied cell is hit, fetching the 8 corners of packed data is both tricky, since the occupancy bits are not one-to-one with the values, and it's expensive, 8 reads and a trilinear lerp. Sure would be nice to use the texture units trilinear. Conveniently, most bricks should be fairly repetitive. No matter how bumpy a surface is, the general orientation of many bricks will be the same. So my idea was to pack the value data into volume texture atlases. Like any atlas packing, there will be a bit of waste, but the hope was that it would be minimal, and this would only be needed for the in-memory representation. The data on disk could be maximally sparse. But if we look at those bricks again, the majority of them could be represented as a height field along an axis. In this example, there is nearly a third less data required compared to an SDF. At this point, there are a couple of realizations that call into question the original goals. By being forced by data size to only store narrowband voxels, narrowband values, there isn't really a field there anymore, is there? My conclusion at the time was that the original goal for this unified representation instead of a dual representation had failed. Thinking about it now, that isn't technically true. For a single level, there aren't values really far away. But if all MIPS are overlaid, every point within the bounding box of the object has value data of some resolution, so long as the root brick is dense. I don't know whether this rapid loss of resolution as the distance of the distance field is still serviceable, but there's even attribute data covering the whole space too, which is neat. I'm not sure if that's useful. The other realization, which I still stand by, is that deciding to retain the source triangles at MIP0, so to speak, the idea that SDFs are needed for magnification doesn't hold up anymore. The source triangles handle magnification. So there shouldn't be a point where voxels get big and look clearly like cubes. Given that, is there still a reason for the SDF data and the SDF intersections inside these cells? Same goes for attribute data. How important is texture filtering in the presence of good AA if there's no magnification? Both of these realizations combine, and the value of being an SDF is seriously called into question. Binary voxels would make things considerably simpler, and the data size would be smaller. No more values on both sides of the surface. So here are the results of that prototype that I made. Never got to that SDF part. I started with intersecting the occupancy bits and would add SDF intersection later. I did get the bound shrinking, but not to the height field part. The coloration in this image is the number of DDA steps. Sorry for the lame test scene. This image scatters the bricks using the rasterizer, and a ray is cast into the brick in the pixel shader. RecList proved to be faster than cubes for rasterizing primitives. The grid gaps that are here are due to a mismatch between the rasterizer position and array position that I never tracked down. It's important to note that these tests did not factor in everything that they should. I only was timing the drawing of the visible bricks. This image scatters bricks to screen space tile lists, and then the pixels run through the list of bricks within that tile, all in compute. Notice that there are no more gaps in this image. Here's the number of bricks per tile. This approach was slightly faster than rasterizing the bricks, but not quite good enough in my opinion. The hierarchical DDA was difficult to optimize. Divergence was a problem with nearly every step having some pixel changing from one level to the next. So I tried ditching the 2 levels and scattering the 4x4 bricks instead of these 16x16x16 2-level things. It was a bit faster, but given I wasn't accounting for the time to cull the bricks, significantly decreasing the granularity wasn't exactly fair. Well, if more scatter is faster, let's go full scatter. Here are point-based rendering with 1 pixel per voxel. It is not as efficient as it could be since I didn't pack the points. It is 64 threads per brick and a thread early outs if the voxel isn't occupied. But holy crap is it fast. This is 2 milliseconds on a PS4 Pro versus 9 to 10 milliseconds for the 2-level brick tracing. 5x faster. I had theorized a lot about point-based rendering, but this is actually the first point I had a prototype with even semi-representative performance. Quality isn't comparable to those other voxel tests though, notice the holes. Okay, well, let's fill in all the pixels that a voxel should cover then, instead of just the closest to its center. To do this, project the cube to a screen space rectangle, iterate through the potentially covered pixels, do a ray versus box intersection test, atomic rate the pixel if it hits. Basically, a software box rasterizer in compute. This fixes the quality problems, but is what is considerably more expensive, 2.5 times slower than the point method. I blame it on the overdraw. On sloped surfaces, voxels stack up. Even the flat ground had considerable overdraw from one voxel overlapping the next. It might be faster to draw the polys of the cube to draw the polys of the cube faces that are on the surface. Besides, how much more ALU is there to test triangle coverage compared to box coverage? Probably less. Now, I didn't think of it at the time, but determining which faces of the voxel that are exposed and which one aren't is trivial. Just check the neighbor in that direction if it is occupied. But at the time, my conclusion was that if the exposed surface of these voxel cubes was turned into triangles, I bet I could rasterize those faster. So it's finally time to try a micro-poly software rasterizer. So now 2 triangles are rasterized per voxel. It's only 70% slower than the blazing fast point scatter version. 1 point versus 2 triangles. Lastly, let's try comparing this to hardware rasterization. Is my software rasterizer really fast, or is this voxel stuff just really slow? Holy shit, my software rasterizer is 16x faster than hardware. The comparison in the final form of Nanite didn't prove to be this large, at least not with real content, but for this stress test, it still might, I don't know. So it's clearly time to pivot. Voxels have too many hard problems remaining. My velocity in solving them is far too low. I believe it would need multiple years of compounding research and industry experience to be able to replace explicit surfaces completely. We aren't there yet, and even if we were, it's unclear if it would be any better. I learned a big lesson in my foray into voxels. Listen to your gut. I never expected this to work, and I only explored it to prove that it didn't. It is nearly impossible to prove something can't be done. Don't do this. Every failure can be followed with, well, maybe if I change this thing. There are no end to the what-ifs. While I wasted far more time on them than I should have, I at least walked away with the thing that I was seeking. I had my solution for pixel scale detail, software rasterization. I probably could have arrived there faster had I focused on the paths that I predicted were most likely to succeed, but regardless, it was progress. So my conclusion. The cubic scaling of volume data is too expensive. Boundary representations are required even with voxels just to manage the data size. This is essentially what only storing the narrowest band data is. I liked what Ryan Schmidt said in the panel about UVs and meshes. I'm summarizing a bit, but he said essentially voxels aren't the 3D analog to pixels, triangles are. I'd add an asterisk to that and say for surfaces. The most elemental atomic unit of surface area in 3D space isn't a circle, it's a triangle. The minimum number of points to bound a 2D area is 3, forming a triangle. The minimum number of points to represent a 3D plane is 3, forming a triangle. Points themselves have no area or volume. They need connectivity to represent a continuous surface, and once you connect them, you have a triangle mesh. Every surface can be turned into triangles, and all I ever cared about was surfaces. It's worth taking a moment here to note that up until this point, only a tiny fraction of the algorithms I explored did I implement any portion of. Of those I did, I only built simple prototypes testing a small fraction of the total algorithm. When the possibility space is vast, efficiently navigating it is essential. Do as much simulation of options mentally or on paper, consider the edge cases, consider it at scale, start with the aspect that is most likely to fail. This is the classic fail fast. Estimating is an important skill. It surprises me to no end how often very technical people make feasibility claims or comparisons based on nothing more than gut feelings when there's often simple calculations that could be done. There are a lot of ways to get data to feed those estimates. Very often, the fastest way to get initial numbers is to find an existing analog that can be plugged into that equation. This might not even come from your work. I have made estimates for nanite behavior using rage videos that had debug stats in them, Dreams reported points per second number in their presentation, and so on. I've predicted the behavior of potential approaches without writing a single line of code. When you need to write code, only write what you need to get the data to answer the most important questions. Code like a scientist. Have a variable in your equation that you don't have any idea what you should plug in? Gather that data. Or write something to help visualize the problem for yourself of where a problem case might be. So when is it time to commit to a path and heavily invest in building it? Fortunately, this is intuition built from experience. But what it feels like is that your confidence in your predictions have grown to the point where you're fairly optimistic about the outcome. You've identified what you think are the solutions to the biggest problems. There is one case that is easy to commit to, and that's anytime there is certainty. The whole point of navigating efficiently is avoiding investing in branches that are useless. But if you know that a branch needs to be traveled regardless, do so because it might teach you something. Do you need to be confident in every aspect before proceeding? Have every detail solved in your head first? Of course not. So what can you delay solving? When describing an idea for an approach to others, I'll often say, I don't know how this bit works, but that seems solvable. What I mean is that I'm reasonably confident that there is a solution to that detail, and whatever it is unlikely to impact the viability of the high-level idea. This again comes from intuition built from experience, but usually is based on how flexible it feels. How many potential options are there? The more there are, the more likely one of them works. Sometimes the details don't comfortably seem solvable. Sometimes there are scary unknowns that could hugely impact the overall viability, and there is no way to know without a working implementation. Here's a few I remember being concerned about for Nanite that luckily worked out. So it's time to venture into that unknown. So I built a prototype, and it's fast, really fast. Initially, everything was drawing down both paths, so the only thing that is Nanite here is just that gray picture-in-picture view. Nothing but a debug view of the visibility buffer, but you can tell that cluster occlusion culling was working. Just after I got the cluster LOD selection, culling, and triangle rasterization working end-to-end for the first time, Rune joins the project, and I have a partner to work with for the first time, and it was awesome. I've been actively R&Ding virtualized geometry for almost a year at this point. I was given a deadline of a few months away to show progress. I expected this was basically a green light meeting. If I didn't have something really promising by this point, my time was up. I don't know if that's the case, but that's how I viewed it. With Rune's help, we delivered something really exciting. This is a shot from that 2019 behind closed doors GDC demo running on a PS4 Pro. Programmable materials didn't work yet. Shadow maps didn't work yet. Streaming didn't even work yet. This shot doesn't even have the hardware rasterizer path working yet, software only. But none of that's important. I knew what this proved. I had finally cracked it. And I wanted to immediately tell the world, but I couldn't. Speaking of, it is worth touching on the emotional side to this. There are many moments throughout this that were rough. I have so much of myself wrapped up in this work that its success or failure is tied to my sense of self. It's not good, but it's real and it might happen to you. Once I have gotten my opportunity to work full-time on this, I thought this was my chance. If I fuck this up, I'm not going to be able to get it again. What if I was wrong? I've talked this up for so long, I've thought about and invested in this problem for so long. Maybe I'm wrong. Maybe I can't solve it. What would I do after this? And then once I had it working, I had the opposite fear. I became terrified that someone else was going to beat me to the punch. Funny enough, key people I was scared of ended up joining the team. This is clearly not the whole story. Graham ended up joining on to help with Nanite development, as did Andrew and Ola to work on shadows. It took another year of hard engineering work by this amazing team of people to go from that early prototype to our first public demo. It took another 2 years after that to get to a solid shippable version for UE 5.0's release. Looking back now, was it luck that it worked? Was Nanite, like I perceived megatexture many years before, an insane gamble, the viability of which was based on numerous unknowns, each one an independent bet, all of which needed to succeed? Was it more likely to have failed than succeeded? Hopefully by seeing the process I went through, it's not as mysterious. I won't deny luck played some role. For example, I was lucky to be given the ample opportunity to pursue this research. But that opportunity would have amounted to nothing had I not been prepared with years of ideas and knowledge that I was ready to jump on when given the chance. I don't know whether I'm unusual in this regard, but this isn't the only background thread I've had going over the years. I have many problems I've thought heavily on, but have not yet had time to work on, and if and when that opportunity knocks, I'll be prepared. The opposite of chance is foresight. How accurate must predictions be? When I was a child, I wondered how my parents could stop the car so precisely. When a traffic light turned red, they would press the brake pedal, and the car would slow down from whatever speed they happened to be going to stop at a line in the road or within feet of the car in front of them. How did they know exactly the right pressure to hit the target every time? How could they be so precise with their foot, within what must have been fractions of a millimeter positioning of the brake pedal? And the initial conditions are different every time. Of course, I know now that's not how it works. It isn't constant pressure on the pedal. Every millisecond, we make new measurements, factor those into new predictions, and adjust the pressure. We adjusted countless details of the Nanite design as they came up, but there were also big decisions that I made based on faulty conclusions, or with a lack of understanding of the true workflow, or with blind spots to future needs. I'm not perfect, and it's hard to say how things would have worked out. So that's my story. That's my story. It has been a long journey. I hope you've learned something about the problem that I've been trying to solve all these years, and maybe you've learned something from my process in trying to solve it. I titled this talk, The Journey to Nanite, as that's the story I have to tell. But the reality is this problem isn't solved yet. Nanite approaches the dream, but does not completely fulfill it. I'm not done working on it, and I don't think you should be either. I encourage you to attack what is remaining along with me, because as I said at the beginning, in my opinion, there is no bigger problem in my field than making 3D content cheaper to create, than making the art of creating it more accessible to more creators, and knocking down every last impediment left to artists manifesting their vision. But I also encourage you to answer Hamming's question for yourself. What are the most important problems in your field, and why aren't you working on them if you aren't already? So, of course, I would like to thank everyone that has contributed to Nanite, and I'd also like to call out specifically folks that I have discussed this problem with throughout the many years. Thank you.
So we have time for quite a few questions. Just raise your hand and I'll come to you.
Sorry, yeah. Hi, Ren. It's a really good talk.
Thank you.
It's a really pleasure to kind of experience it together with you. I was wondering, you mentioned about the hardware, software rasters, and so on, right? And the hardware rasterization is currently designed to solve, the classical kind of assumptions, right? The old assumptions about the content, right? The triangle size and so on. So do you think it's time to revisit it? Do you think it's time for another acceleration? Because at the end of the day, hardware is just accelerating things, right?
It's hard to say. I mean, first up, I'm not a hardware person. So I'm not sure as far as how much transistors are going to be required to make a micro-poly rasterizer specific for that. And regardless of how many that is, whether those would be best served by making fixed function rasterizer hardware, or whether it would be better served by just giving more compute power for us to be able to write one in software. As far as where that energy and power trade-off comes, it's hard for me to say. I'll say it's working pretty well right now with the scheme that we're doing. If such a thing would be created, I think the only way that it could be successful is by making the same concessions that we did, which is don't make it flexible. It only works for a very constrained case, and then the user would have to commit to those constraints and understand and send only the geometry down that path that can meet them. But even under those under that guideline, it's hard for me to say.
Thanks.
Maybe just to follow up on that, what is the average triangle size in pixels for your seed?
That's a good question. So it is not as small as I expected when I was doing that prototype. So I don't remember whether I've got a thing in here on it or not, but
The very first, on your title slide, it seemed like it's pixel size, but maybe it's not.
well, we've talked about how fast we draw pixel-sized triangles, but the average is not pixel-sized. So there was a point early in that prototype where after I'd written that test of switching the voxels over to triangles, and it's like, wow, this is really fast. This totally fits in the budget. Every single one of these triangles being the size of a pixel. Much later on, I learned more information about that once we had a more complete system. But fairly early in the prototype, it proved that it was faster so what I thought I was going to be making when I set out to start that prototype was I was going to be going for exactly pixel-sized triangles, and they were going to be fairly uniform sized because I thought the divergence in the software rasterizer would be really bad if there were triangles of both small and large all mixed together. It turned out not to be the case. It turned out to be faster to have less triangles of arbitrary size than more triangles that were all uniformly sized. That also had the benefit of decreasing the amount of memory. So just the amount of cache for the triangles that need to be in memory are now, they both come out to the same amount of memory, whether they're uniform or irregular. So like as soon as I got the evidence that it was pointing towards, oh, it's actually faster to render these being arbitrarily sized, and they're like would be considerably less memory, just like committed down that path. I've recently, through some other research, looked at that decision again and saw just like, well, what would it take if if we did dense and now I have a more complete system to actually do the tests against, and it's just if we needed to draw all the pixels with pixel-sized triangles, it would not fit in our budgets, not on this hardware. So to answer the question you actually asked, I'm not sure I've got a number for you, but triangles that are, I'd say the average is somewhere between 4-8 pixels wide. How many actual pixels of area, how many pixels area that are inside that triangle? I'm not sure I could give you an accurate number, but something more in that ballpark, covering maybe 10 pixels in total, 12 pixels, I'm not sure, on average. But what I guess when we say that we can draw pixel-sized triangles very fast is because some of them are, but they aren't on average.
Essentially, the ray tracer becomes a hole filler. You have your samples, and essentially it just fills the holes consistently. Is that a way you?
It's not a ray tracer.
Sorry, the rasterizer. Sorry.
I suppose you could think of it that way.
Hi, thank you so much for the talk. So I was actually wondering, in your presentation you mentioned that you got a speed up from doing Z buffer occlusion culling, like in between frames, I think, like in order to prevent or reduce the number of draw calls between successive frames. So my question is, how much of a speed up is this? Like another related question is, how much transparency can you handle before like this sort of Z buffer culling becomes like too slow and it's no longer like fast?
So I didn't really talk about occlusion much in this talk. I could still answer the question though. Occlusion culling is vital for being able to get things fast. Like the concept behind what the high-level view of what Nanite is trying to do, and all of these schemes are trying to do it in one way or another, is to make the cost scale with the resolution of the screen. So number of pixels on screen is roughly the amount of cost. The level of detail is one way to get there by making it so that we've got triangles that are average this same sort of thing. No matter what you're looking at, we consistently have a similar sort of average triangle size. But it also means that we can't have pixels getting hit by many triangles on top of one another. So getting down to as perfect of hidden surface removal as possible is key to being able to have that property. Now, we don't do it perfectly. We don't do either the lotting or the occlusion perfectly. There's some amount of waste, so there ends up being a multiplier over what the number of triangles that we draw is actually quite a bit more than the number of pixels on screen. But it continues to be somewhat consistently proportional. And if occlusion culling wasn't there, that would scale completely unbounded. Like, depending on what you looked at, it could be an overdraw of 1,000x, or it could be 1. So that occlusion culling is vital. The second question is about translucency. And maybe I'm not understanding you, but Nanite does not support translucency currently.
Yeah, I was wondering because, since you mentioned it becomes unbounded, I was wondering, like, is there like a point, like how many, can you only have like a little bit of transparent triangles before it just becomes completely like way too slow, or is there like a limit, or is it just no transparency at all?
There's no transparency at all currently, because we are writing out to a visibility buffer, which is, it's like writing out to a G buffer or a depth buffer. There's not multiple samples as far as stacked up in depth. So yeah, there's just one entry per pixel in the visibility buffer. We could support, in theory, doing all of the rest of the data structure, traversal, LOD selection, that sort of thing. Switch off the software rasterizer, only go down hardware rasterizer such that we can write out, such that we can use the blending units, and could support translucency in theory. It's not really a priority for us right now because it's translucent things don't tend to need super high poly stuff or have tons of draw calls in the scene. We don't have use cases that really necessitate that sort of thing, and there's a number of things that it turns off such that they would probably be pretty slow to render anyways, so we could support it in theory, but it's like not on our lists right now to work on.
Okay, that makes sense. Thank you.
Hi, you talked about the topology problem and how some surfaces with high number of holes can be problematic in many approaches. But because Nanite works on connected patches of triangles, did you actually get to solve that?
I missed a couple of things in there as far as like lots of holes, and are you talking about the occlusion problems with the multiple holes?
No, the high genus problem.
The high genus problem. Nanite doesn't have that issue because it doesn't have any constraints on the genus. While for correctness reasons, a edge collapsing, mesh decimation, mesh simplification, whatever you want to call it, doesn't necessarily do correct things if you keep on collapsing past the point where the genus changes. We allow that to happen, and it's important to let it happen to get it to continue down and get past these sort of genus constraints. There are more smarter things that could be done in a mesh simplifier to do things that aren't just surface level edge collapses, that could do other things that could completely change the genus. We don't do anything other than edge collapses at the moment. I've experimented with some other things. Some of them are harder than some of the literature out there makes them out to be, but there's a different scheme that I have in mind that I think will solve that, but I haven't gotten to it yet. But yeah, it's because each one of those things is just an edge collapse. Like we can take something that's like, think of like a thin wire, a thin cylinder. We can collapse the edges down the middle such that it pinches to just a single point. We can have it where 2 points get pinched down so that all there is just single, zero width edge in between them, and then the simplifier sees that and says like, oop, gone. And now you've just disconnected two things that were together. We could have a hole in the middle that is like collapse, 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 and then the hole closes on itself. So it can end up doing those changes just through its process.
Brian, I have a question.
Mm-hmm.
At what point in your journey did you learn about hardware ray tracing, and what kind of spanner did it throw in your progress?
So I was asked to remove some of those details from these slides by my boss to be courteous to the relationships that we have with IHVs as far as when we learn information and when we don't. So I guess I'll answer that as vaguely as I can get away with. There were points at which obviously, I worked on that Star Wars Reflections demo, and that was through this process. So it landed somewhere in there. It's not like I only learned about it after everything was done. And there's also points at which we're disclosed on information about hardware before we would necessarily have one in our hands. So it's kind of hard for me to answer that without stomping. I had some of those, I mentioned some of those things in my slides, and I was asked to take them out. Actually, I'll add one extra detail that I could probably get away with saying. I can say factually that I did not have any sort of hardware ray tracing hardware. I didn't have any RTX card. We hadn't started on that demo yet. For something that I had a piece of hardware that I could test with and get any sort of information about that, or any sort of information about the hardware ray tracing support coming in the next generation of consoles. I either had nothing or knew nothing at some of the times when I was doing those evaluations. And at the times when I did start having it, I was down a route that already had some stuff. So that's that's a vague answer, sorry.
Right along those lines, how do you think you could support ray tracing effects, like reflections at least, in something like Nanite? Would you?
We would love to. Well, so we do-ish. We support, Lumen can do hardware ray tracing at the same time that we're using Nanite in the scene, but that hardware ray tracing is not ray tracing the Nanite data structure. We make a separate proxy mesh that's just a traditional index buffer, vertex buffer, so that the hardware has the thing that it expects to use. We don't have any of this fancy virtualization streaming stuff. It's not using any of our compressed data formats. It's just completely here's this side thing to make that work. So we can have them going at the same time. I'm sure you weren't asking that. You were asking how to ray trace the actual Nanite data structure. That's something that we've done some experiments with, and there we go. Got some guys over there who are working on that right now. So it's in the process. There is a lot of challenges though that come up. So if you are an IHV and we haven't already talked to you, which I'm not sure who that would even be at this point, on this problem. There's a lot of challenges of just updating. So if you want to have the BVH over the clusters and swapping out clusters as they stream in, you now have to update a BVH that could be very deep. You could have the currently resident version of that mesh and its resident highest quality version existing in memory. Could be a million triangles, and then updating the blast for that as one bit of it changes could be a very expensive rebuild from scratch operation when only a portion of it has really changed. So having updates on stuff like that is important. There's also the instance side of things. So that Moana Island scene is insane in its instance count, but we've got scenes like the Matrix demo that aren't 27 million, but they're 1 million or 2 million or something instances like that. And if you wanted to rebuild the TLAS every single frame, like what is typical, and you're doing it with that sort of instance count, you're chewing up a big portion of your frame to rebuild, once again, something that maybe only a subset of the scene is actually changing from one to the next. So there's stuff like that that may help, but then there's other just challenges of, if you were to just convert the Nanite triangle format to something that was like DXR ray traceable, the size of a triangle for how we have it encoded in our custom format and what the encoding is that the hardware expects, that encoding with its, its box nodes and the triangle format and all that stuff is considerably heavier. So that's another part of the complication that's not just about the updating of things every frame, but it's just the pure just memory side of it. So all of those things are things that we're trying to balance in some of these prototypes of where should we draw the line? How, should it be just completely, just all of it up to the highest detail level to try to fit in memory? That seems like too much. Well, if we don't put any of it going through hardware acceleration, then that's a waste and is going to be slow. So at what point should we do that? At which point should we drop down to just a software test in the intersection shader to try to get that to be as fast as possible, but as minimal amount of memory? Exactly where that lands is still in the works.
Hi, Brian. Great talk, first of all. So you were talking about your rasterizing these micro triangles, over pixel centers, and I was wondering how you ended up dealing with the problem where poles get sub-pixel off in the distance, and it just turns into a kind of anti-aliased mess or an aliased mess.
It is a problem. The aliasing that the high poly geometry caused specifically for this matrix demo was brutal. Guillaume, the engineer that was working on our temporal super resolution algorithm, went through a great deal of pain to try to improve that. At the start, before I got into the weeds of Nanite actually working, I was anticipating that we should be pre-filtering the geometry like we pre-filter textures with the Tokesbig stuff, that sort of thing. And I thought, well, I can, as it simplifies, I can pre-filter the vertex attributes, I could pre-filter normals, I could store a roughness, I can do those sorts of things in object space. Now, some of that is just not pre-filterable unless you also store opacity. You're not going to be able to pre-filter visibility itself without it, but you could pre-filter the shading attributes. There's it's more than just specular pre-filtering, because the places that we see a good amount of this aliasing is actual diffuse differences. It's light to dark on, if you just think of just a grading. And trying to get that filtered out needs to have that sort of level, which isn't necessarily just putting roughness on a rough diffuse model. You really want it to be more convolved over world space. It's been something that kept on expecting, I'm going to need to get to that, and it just hasn't been a priority so far, so we don't have any pre-filtering in there right now. There's a trade-off that has kind of steered us away from that unless absolutely necessary, and it hasn't been absolutely necessary yet, which is it will add data. Any amount of that pre-filtering, if I've got to store roughness in there that wasn't previously there, we've now increased the vertex size for all of those meshes just to deal with that. And many times when this comes up, it just seems like I don't know if pre-filtering is going to solve that. It's just bad. So far, kicked it over to the anti-aliasing side and forced Guillaume to deal with it. But it was pushed to the point of being basically unsolvable on the Matrix demo, and he did a valiant job of trying to deal with it. But there were major cases where, to try to describe briefly, the thing that caused him the worst problem was these moire patterns, where it wasn't a matter of just like, oh, here's this one thin edge and we need to, or this little firefly to get rid. Instead it was, all of these slats are bright, all of these slats are dark, and you don't know the difference between that aliasing pattern and an actual change, like an object moving in front of it, or the lighting changing. So to make the TAA responsive to those sorts of shading changes was running in conflict of dealing with this ridiculous extreme level of aliasing that we just hadn't had content for before. But that's where we are so far.
We're almost at 9 p.m. So let's thank Brian again for a wonderfully inspiring talk. And also thanks to everyone for showing up. This has been a much larger attendance than we expected, and it's clearly been really worth it. Thanks again.
If anyone has any more questions, come and ask me afterwards. Thanks.
Oh, great, yeah.